And we are live. Assalamu alaikum, everyone. Welcome again to the fourth batch of AI Summit. We're coming with new conferences, some very interesting topics. And today we are having Nazim Bendib. First of all, Nazim Bendib is a graduate from Easy Algiers from the Intelligent Systems and Data option. He's also currently having a studying masters in Sorbonne University and a research intern at Emilia in Sorbonne University, as well as an NVIDIA ambassador. And most importantly, I believe that is Nazim is one of the key founders of School of AI and one of like the people who've been in School of AI since its first years up till his graduation, and also now like giving conferences in AI Summit. مرحبا بك Nazim Bendib, and the mic is yours.
شكرا صح كمال. Assalamu alaikum everyone. Hello. I hope you're doing well. I'm so excited to present once again with School of AI. Inshallah every year نديرو des petites présentations هكذا. Today I'm going to present something that is very new to me. And the moment I heard of the topic, I decided to do a workshop about it. I wanted to present it to other people because it's a little bit weird. It's called Unsupervised Reinforcement Learning. So in the very beginning, we thought that we have like AI and then we have some paradigms, mainly supervised learning, unsupervised learning, and then reinforcement learning. But inside reinforcement learning, there is another topic called unsupervised reinforcement learning. Which is pretty cool, I thought. It's a little bit confusing and difficult, but I will try to make it as easy as possible. So if you want me to start, can I go?
Yes, you can start. Yeah.
Okay, perfect. So in the following presentation, I'm going to start with a small introduction to remind people about what is reinforcement learning. We will try to talk about the different components, and then we will scale in difficulty and talk about what is unsupervised reinforcement learning, which is basically an extension of RL. And the goal of this presentation is to introduce you to the different methods that we use in unsupervised reinforcement learning. It's actually a very, very active field of research. And what I'm going to show you is just the most famous methods in the field. So there are actually a lot. I'm just going to present 4 of them, which are basically like the key solutions. And I think they are the easiest one to understand. All right. And so in the methods, we have the skill discovery methods and we have intrinsic motivation methods. And by the end, it's going to be like small conclusion. So a reminder about reinforcement learning. So maybe before even going to this, we know that we have the field of artificial intelligence, which is like very, very broad. And inside it, we have what we call machine learning, which is basically building algorithms that are going to learn on their own using data that can be collected by humans or collected by the model itself. And inside machine learning, we have different paradigms. So the very first one that comes to mind is the supervised learning paradigm, where we have a model and we have data sets, and then we just train the model over the data set to predict classes, for example, or predict numerical values or whatever. So this is like the easiest case, I would say, because we have the data and we just want the model to mimic the data in a way, to learn the patterns, but it's actually more than that, because we want the model to not just memorize the data, but to generalize after. And then this is called supervised learning because we have a supervision. So we supervise the model using the dataset, but then we have what we call unsupervised learning, where we don't have datasets, and actually, we can have a data set, but we don't have labels. And the goal is to train the model using only the inputs without having access to the ground truth, to the correct outputs. And that's a little bit more difficult because we don't have a supervision, we don't have a feedback, And we have like quite a lot of methods in there, but we're not gonna talk about that. And then we have what we call semi-supervised, which is basically a mixture between supervised and unsupervised. Let's forget about that for now. We have self-supervised, which is basically a fancy way to solve unsupervised learning tasks using supervised learning methods. And here we have reinforcement learning, which is a bit different because we have like different components, but like the core of the solutions is basically the same. So in reinforcement learning, we have an agent mainly, and we have an environment. And the agent is going to interact with the environment, and the environment is going to give rewards or feedback to the agent. A very basic example that I love to give to people is Super Mario. So you have Super Mario, you have Mario that is playing the game, and the environment is the whole game, and the agent is Mario. And the goal of the agent is to go through the whole episode, through the whole environment, through the whole level to reach the flag, and then you go to the next level, etc. And so at the beginning, the agent doesn't know anything about the task, doesn't know anything about the environment, and so it's going to take random actions. For example, in Super Mario, we can jump, we can like fall in the holes, we can hit turtles, etc. And in the beginning, the agent is very bad at the game. It's hitting turtles all the time. It doesn't know where to go exactly, etc. So it's quite hard. But then using the feedback signal from the environment, Mario is going to try and avoid turtles, jump over the holes, eat the mushroom because it gives you more power, so you're more likely going to end the episode until it reaches and solves the problem. So maybe an easier example is you have simply a maze, and you have the agent, which is basically a dot in the maze, and the goal is to solve the maze and get out of it. And so, the agent takes an input, which is basically the observation or the state, and is going to predict an action. In the case of a maze, the actions can be going up or down or left or right. In the case of Super Mario, it can be jumping, moving forward, moving backward. What else? I think that's it. Maybe crawling, I don't remember. But these are like the actions. And we have the action, we apply it on the environment, and the environment is going to return two things. It's going to return the next state, which is like the updated observation. If we are in a maze and we move up, then the state is going to be different because we're going to see maybe new walls. We're going to be in a different position, so it's a new state. And like in addition to that, it's going to return what we call a reward, which is basically a feedback. Now, a reward is most of the times a scalar, عدد حقيقي, a number réel, which is generally positive when the action was good and negative when the action is bad. In the case of a maze, if we hit a wall, then the action is bad. So the environment is going to return a negative reward because it's a bad action. But if we reach through the end, then the environment is going to return something positive because it's a good action. And the goal of the agent is to actually maximize the reward, or maximize what we call the cumulative reward, which is basically the reward over the whole episode. And that's how the agent is going to learn how to solve the task. In the case of Super Mario, then if the agent hits turtles, then it's going to get a negative reward. And if it eats the mushrooms, for example, it's going to get a positive reward. And if it finishes the episode, it's going to get an even higher reward. And so the agent is going to try and maximize the reward. So it will learn to avoid turtles, because hitting the turtle is going to give you a negative reward. So that's bad. So the agent is going to learn how to avoid that. And it will try to eat the mushroom, because mushrooms gives you a reward. So we want that. And we will try to solve the episode by the end. And that's how we train agents in the reinforcement learning paradigm. Now, the components, we have the state, which is basically the representation of the current configuration. The action is what the agent is able to do in the environment. It's how we move, what we can control, basically. The environment is the game, it's the maze, it's the problem kind of that we want to solve. And the reward is the feedback signal. So when we say feedback, we say supervision, and we can say that reinforcement learning is maybe a fancy way of doing supervised learning. Because in supervised learning, we have the grounded truth. We have the feedback signal. We have the signal that we can use to update the agent. In unsupervised learning, we don't have that. In reinforcement learning, again, we have that because we have reward coming from the environment. And so there is a feedback for the agent. Now, in unsupervised reinforcement learning, spoiler alert, we're not going to have access to the reward from the environment. And so there is no feedback coming back to the agent. And that's the whole thing. So let me just go to the next slide. So yeah, maybe before talking about unsupervised reinforcement learning, let's talk a bit about what we call goal conditioned reinforcement learning because we can use it later. So traditionally in reinforcement learning, we have an agent that is going to take the input, which is basically the state, and it's going to predict an output. In goal conditioned reinforcement learning, it's a bit more sophisticated. So the agent not only is going to take a state as input, but it's also going to take a goal as input. And so in Super Mario, there is only one goal. It's to finish the episode. And so there is no need to pass a goal to the agent because it's always the same. But for example, when we have problems like this, can I maybe... I'm having a small problem. I was expecting to be able to draw with my pen, but apparently if I share on StreamYard, I can't do that. Yeah, whatever. In goal conditioned reinforcement learning, it's a bit more developed. So imagine that we have a maze, and in this maze, there is no like a door to go out. So we can ask the agent to go to a specific place in the maze. So for example, if we are here in the middle and we want to go to the red dot, then the agent is going to need to select the best actions to go in there. If I want to go to somewhere else, for example, in the orange dot, then I need to be able to do that. Okay? So yeah. Why do we need it? We need it to leverage or to generate different behaviors. So we don't want to have an agent that is able to do one task. We would love to have an agent that is able to do multiple tasks. That's like more human-like, that's more desirable, and that's what we want in our machines. So GCL or goal conditioned reinforcement learning enables multi-goal learning, generalization, and reusability of policies. So you can have the same policy that is able to solve multiple tasks, allowing agents to solve a wide range of tasks without retraining for each new goal. So you can have one agent to solve all goals instead of having one agent per single goal. So that's goal conditioned reinforcement learning. Okay. All right, so the goal, like the ultimate goal, is to have a policy or an agent that is able to learn as many different behaviors as possible. Imagine having an agent that is only able to have one single behavior. It's boring, it's not desirable. Generally, we don't want that because we want something to generalize. We want something to be able to do multiple things. And we call this a behavior. So what is a behavior? A behavior refers to the observable sequence of actions and states that an agent can reproduce. So we can basically represent behavior as a trajectory of actions and states. For example, if I go back to the previous slide, then if I go to the sequence that takes me to the red dot is called behavior, that is different to the sequence that takes me to the orange dot, which is basically a different behavior. And so the goal is to maximize behaviors, right? In traditional reinforcement learning, we're not able to do that because we only train the policy to follow one behavior. So yeah, the ultimate goal is to maximize diverse optimal behaviors to ensure effective exploration, skill discovery, or task performance. And this brings us to unsupervised reinforcement learning. So in unsupervised reinforcement learning, we don't have access to the reward function from the environment. So we don't have access to the reward, which we call the extrinsic reward because it's something external to the agent. And not only that, but we want to learn different behaviors. So I don't know the reward that I need to maximize. So to solve this, I will try to learn as many different behaviors as possible so that once I have access to the reward, I will just use one of the behaviors that I've already learned. So basically that's it. So as definition, it's a learning paradigm where the agent explores and learns useful behaviors or skills without access to the external reward signals or task-specific supervision. So why do we need it? We need it because sometimes having access to a reward is quite expensive and it's not always available. So if we, for example, take an example of code optimization, so the goal is to choose the best sequence of optimizations to optimize a certain code, then the reward to calculate it, we would need to calculate the execution time of the code, which can be a bit costly because sometimes we have a code that takes a lot of time to run. And so if we execute the code every single time to get a single reward, that's not very effective because it's going to slow down the whole process. So that's just one example. So yeah, we try to put ourselves in a much, much harder problem. We say, all right, no access to an intrinsic reward. We will try to learn as many behaviors as possible. And hopefully, once we have access to a reward function, we would only use one of the behaviors that we learned. And so that's why we try to maximize the diversity of the behaviors. So, okay, why do we need it? Unsupervised RL helps agents acquire general purpose skills, explore efficiently, and bootstrap learning in environments where external rewards are sparse, delayed, or simply unavailable, making them better prepared for downstream tasks. Okay, so that was a little bit of an introduction. Now, we know what is unsupervised reinforcement learning. We know how difficult it is. We know why we need it. Now we need to see how can we solve such a problem. Now, in the literature, like, as I said, it's a very active field of research, and researchers came up with like a lot of brilliant ideas. I mean, it's just fascinating. It's what made me fall into this field. So, I tried to separate the work into 4 different subfields. The very first one is called skill discovery. The second one we call intrinsic motivation. So as a reminder, the reward that we get from the environment is called the extrinsic reward. And here it's called intrinsic motivation. And it's very cool. We have what we call state coverage. And by the end, we have what we call unsupervised goal conditioned reinforcement learning. So in the skill discovery one, the goal is to learn different skills that are very, very diverse. And we are going to present each skill using a latent variable. So we are going to condition the policy or the agent using a latent variable that is going to generate or produce a very distinguishable skill. So this is a skill discovery, and we're going to spend most of the time talking about this. We have what we call intrinsic motivation, which basically says that as human beings, we don't really need an explicit goal to solve a task. For instance, if you take babies, when you have a baby, you put it in a room and you put like a lot of toys around it, then the baby is going to try and reach for the toys, try to do some sort of experiments, throw things, push things over the table. And so what made the baby do this, it's called the intrinsic motivation. So there is a motivation behind everything that a baby does. And basically neuroscientists found out that in a baby, there is some sort of, how do we call that hormone? A dopamine. There is some sort of dopamine reward that the baby gets whenever it reaches a goal. So basically, this is how it works. We have a baby. It's going to set a goal like randomly. And once it reaches the goal, it's going to get a dopamine dose, which makes which makes him happier, kind of. And the same thing happens with cats. You know, if you take a little cat, it's very energetic, very active, plays all the time, runs over stuff, etc. And it's for the same reason there is some sort of a dopamine reward which enables the cat to do all sorts of messy stuff. And alhamdulillah, I mean, thanks to God we have this, because otherwise babies or little kittens won't be able to learn anything about the world. So they need to have some sort of motivation that motivates them to explore the world. And researchers got inspired from this, and they have like subfield called intrinsic motivation, where they try to kind of let the agents motivate themselves. So whenever the agent learns something new or a new behavior, it's going to get some sort of intrinsic motivation or intrinsic reward, very similar to the dopamine dose that the baby gets. We have also the state coverage. So in state coverage methods, the goal is to try and explore all possible states. So we try to maximize the states that we explore. And by doing that, we are going to learn very, very different behaviors. And by the end, we have unsupervised goal conditioned reinforcement learning, which basically let the agent select goals to reach. And once it reaches the goals, it will try to reach like further goals, etc. And all of this in unsupervised fashion. So maybe before going forward, when we say that we do unsupervised reinforcement learning, it doesn't mean that we don't use a reward, but rather we don't have access to the environment's reward. But the goal basically is to kind of engineer our own rewards to, for example, motivate the agent, to let the agent produce distinguishable diverse skills, etc. So when we say unsupervised, it doesn't mean we don't have a reward at all. It just means that we don't have access to the extrinsic reward of the environment. But each subfield is going to try and generate its own intrinsic reward. And we're going to see that in a moment. All right, so in skill discovery, as I said, we have multiple methods, but before moving on, let's just define two things. We have what we call entropy, and we have what we call the mutual information. And in the skill discovery, they abuse this, like they use it a lot. And so I thought that maybe I need to cover this before moving on. So the entropy is basically the measure of uncertainty. It's a measure to kind of tell whether a random variable is very, very random, or which means it's very uncertain, or something that can be uncertain. So basically, if we take an example, if we have a die, okay, and it like has 6 dice, so ND, and then we throw it, and then we see which face is showing, then each face is going to have a probability of 1/6, which means this random variable is very, very random, which means it has a high entropy, okay? Because there's like a high uncertainty. We can't know beforehand which face is going to show. All the faces are having like the same probability. And for matter of fact, this is called a uniform distribution, and a uniform distribution maximizes the entropy. So we can't find another probability distribution that has a higher entropy compared to the uniform distribution. Another example, imagine if you had a base coin, and when we throw it 99 times, it's heads, and only 1 time it's tail. And so this event is kind of very certain. So when you throw it, you can just guess, yeah, it's going to be heads. And so it's not uncertain, it's very certain, and that's its low entropy. Okay, so high entropy means high uncertainty, low entropy means low uncertainty or high certainty. I hope this is clear. Now, we have what we call the mutual information, which kind of builds over the entropy. So the mutual information measures how much knowing 2 variables tells you about, knowing 1 variable tells you about the other. So the mutual information, we calculate it between two variables compared to the entropy where we only calculate it using one variable. Okay? So it's going to be easier with an example. Imagine if A is the temperature in Celsius and B is the temperature in Fahrenheit. Okay? And we try to calculate the mutual information between them. It's going to be very, very high because both variables are very related, and so they share a lot of information. Okay? Another extreme example, if we say that A is your shoe size and B is the daily temperature in Tokyo, then these two variables are very non-related. And so the mutual information is going to be very low because basically they don't share any information between them. Okay? And so, yeah, this is the mutual information. This is just a small visualization in here. You have variable X and variable Y. Okay? And so the intersection between them is kind of the mutual information. And yeah, we denote it as I of A and B. So this is the mutual information between A and B. And for the entropy, it's H. It's like in here. So H of X is entropy of X. And the mutual information can be defined using the entropy. Yeah. So the mutual information between X and Y is basically the entropy of X minus the entropy of X given Y. And it's commutative, so we can do it like the other way. It's the entropy of Y minus the entropy of Y, given that we know X. And this is going to be very useful later on. All right. So yeah, this is the idea in skill discovery. So in skill discovery, we want to learn skills, or we want to learn a policy conditioned by skills that is going to maximize the mutual information between behaviors and skills. So what does this mean? It means that if we condition the policy on certain skill, then it's going to generate a behavior that is very distinguishable, that is only associated with this skill, and it doesn't look like any other trajectory. And this is basically a maximization of the mutual information. As you can see here in the examples, these are environments, like very famous ones. This one is called half cheetah, which is basically, let's call it a robot with multiple joints, and it has like one arm and one leg. It can move. So traditionally, it only needs to move forward. But since we don't have a reward function, we will try to learn different behaviors. And so in here you can see that we can either learn a skill that makes the agent moves backward, move forward, we can stay still, or we can kind of crawl like this. So it's like it puts the face on the ground and kind of only walk or crawl with the arms without using the legs. So these are like 4 different skills. And now once we have access to the real reward, then yeah, we can just pick this second skill because it lets the agent move forward. Okay? These are other examples. This is called Ant. And so it can jump like in different directions. It can do like some sort of flips. This is Hopper, so it can like jump. So here it's jumping backward. Here it's jumping forward in much faster way. So these are just like different skills. Okay, so yeah, the very first one, which is basically the paper that opened the gates of unsupervised reinforcement learning to me, is called DIAN, which basically stands for diversity is all we need. It's very, very famous in the literature. It's authored by Kim Eisenbach, which is like very famous, and co-authored by Sergey Levin, which is basically the godfather of reinforcement learning. So it's really the good stuff. And so DIAN is an unsupervised reinforcement learning method that learns diverse behaviors, basically what we've been saying from the beginning, without any external reward function, of course. And it does this by encouraging the agent to learn skills that are distinct from each other and consistently repeatable, like not random. Okay, so now each skill needs to have its own distinguishable behavior. And given a skill, we are not allowed to generate different behaviors. We are only allowed to generate that same behavior. So the skill here is kind of a random variable, and the behavior is another random variable. And we try to maximize the mutual information between them. So Diane wants to learn a set of skills Z, such that each skill leads to behavior that is distinguishable from the others. To do this, Diane maximizes the mutual information between the skill and the states that are visited. So remember that in here, we said that we try to maximize the mutual information between behavior and the skill, but it's quite hard to define the behavior, find a very appropriate behavior. So in Diane, they took shortcuts. They said that we're not going to maximize the mutual information between the skill and the behavior, but rather we will maximize it between the skill and the states that are visited. Because we can kind of represent a behavior using the states that we move through. So that's the idea. And basically, it's not just that. They go a little bit further. So this is the objective function that they try to maximize. It's mutual information. Oh, I can have laser points. Good. So basically, it's mutual information in here. Okay. Mutual information between S and Z, plus we try to maximize the entropy of the actions, domain states, minus the mutual information of the action and the skill given the states. So we will try to maximize this and this, but we want to minimize this. And let's try to understand what the hell is this. So we have 3 terms in the objective function. Okay. The very first one, don't forget that we're trying to maximize this. So the very first term is just mutual information. We try to maximize how much knowing the skill tells us about the states that the agent reaches. So this is like the basic one. But at the same time, we want to encourage the agent to try different actions in the same state. So we said that the entropy is just a measure of uncertainty. And if we try to maximize it, it means that we try to maximize the uncertainty, right? And so this here says that if we are in a certain state, then I want my agent to be able to generate as different actions as possible. Okay? We try to maximize the entropy of the actions given the states. Minus the mutual information of the action and skill given the state, which means that we will try to minimize this mutual information, which is basically minimizing how much the skill influences the action at a given state. Because if you are in a certain state and we have a skill, then we are not allowed to choose like many different actions. There's just like one particular action that we need to make. Because as we said, given a certain skill, we would want the behavior to be as distinguishable as possible. We don't want to have like intersections kind of between the behaviors. So that's why we try to minimize this mutual information. But working with mutual information is quite hard. So what they does is that they develop stuff using the formula that I showed you. And this is like the final objective function. So we can try to understand this, but it's easier using the mutual information. So basically here, they will try to maximize the entropy of the skills to learn as many different skills as possible. And they will try to minimize the entropy of the skill given the state, which is a bit weird. And then they try to maximize the entropy of the action given the state and skill. So it's a mess. It's easier to just understand the first formula. All right. So again, once we have this, the problem is not solved because we need to develop a little bit more. So they use something called variational lower bound estimation, or basically it's ELBO. And it's the same thing that is used in variational autoencoders. So basically, they go from this to this. Let's not go over the math. And by the end, they say that, oh, this is similar to policy gradient methods, like in PPO and stuff. So once they saw this, they said that, yeah, it's very similar to traditional reinforcement learning. And basically, we can take this as a reward that we try to maximize. And that's exactly what they did. This is the intrinsic reward that I are using. It's basically the log probability of the dynamics estimation of the scale given S minus the log probability of Z. And there is still this term, and for this term, it's basically maximizing the entropy of the action, which is already done using an algorithm called soft actor critic, because in soft actor critic, we maximize two things. We maximize the reward, and we also try to maximize the entropy over the actions. And so they saw this, and they said that, yeah, this is very similar to soft actor critic. This is just a reward that we try to maximize, and this is just the usual action entropy maximization. And they did this, and this is Diane. So basically, this is just a pseudo algorithm. All right, so they sample an action. So first they sample a scale, okay, from distribution of scales. And they say that we can have something like as a Gaussian. So it's like in GANs, we have a Gaussian distribution and we just sample scales from them. But they said that it's easier to discretize stuff. So let's say that we have 10 discrete scales represented using one-hot encoders. And so we have, like, for example, scale 1, scale 2, scale 3, until scale n, which is like a finite number. So first we sample a new scale and a new initial state. And then basically we just follow the policy condition on this scale and we generate the actions. And then from the action, we are going to just apply it on the environment to generate the next state. And then we compute this using the discriminator. And it gives us the reward, which is basically following the previous formula, which is this one. And then we try to maximize it using soft actor critic. And by doing that, we enable the agent to learn scales that are very, very distinguishable. Maybe you can take a look at the diagram in here. It wasn't very useful to me, but we have what we call discriminator, which is this. It's basically an estimation. And we have the policy. So basically the policy is going to select actions, perform them, or apply them on the environment. The environment is going to give us the next state, and then we are going to calculate the discriminator value using this next state. And using this, we are going to calculate the intrinsic reward that we are going to pass to the policy to get updated, and we keep doing this. What's really cool is that we're not using different reinforcement learning algorithms. So soft actor critic is pretty famous. So it's basically the same. What we change is just the reward that we try to maximize. And that's something that is very important because it doesn't take a lot of implementation to do something this sophisticated. Okay, so this was for Diane, diversity is all you need. Now there is another paper called DADS, or basically Dynamics-Aware Unsupervised Discovery of Skills, which I think was also authored by the same team. So they revolutionized reinforcement learning, basically. And so in here, they also try to maximize mutual information, but this time it's the mutual information between the next state and the skill given the current state, which differs a little bit compared to Diane, because in Diane, we try to maximize the mutual information between the state and the skill. All right? But here they add this condition. So we were conditioning the whole thing using the current state. All right, so again, they developed the mutual information into this, and they chose this. So basically, we try to maximize the entropy of the next state given the current state, and we try to minimize the entropy of the next state given the current state and the current scale. And this is kind of easier to understand because in the first term, it means that if you are in certain state, without knowing which scale I'm using, then I would love to explore all the next states, right? So I try to maximize the entropy of the next state given the current states. But if I know the skill that I'm using, then I don't want to have a lot of randomness in the next state, but rather I want to be sure of the next state that I'm going to choose. And this is basically in the second term. So it's just saying that if I don't know the skill that I'm using, then yeah, I want to maximize the next states. But once I know which skill I'm using, then I want to be sure of the next state that I'm going to. And this is like the objective function of that. And they further develop this using variational lower bound, the same way as Diane. and they end up with something like this, which is basically very similar to policy gradient methods. So it's just an expectation over something that we try to maximize. The problem is that, yeah, we have a discriminator in here, which is parameterized, no problem. But this probability here is intractable. So since we don't know the dynamics of the environment, so this means that it's a probability of going to the next state knowing the current state. Now, if the environment is deterministic, then it's not about deterministic or not. Because if you want to calculate this probability, we need to have access to the actions. So to calculate this, we need to integrate over all of the actions. And it's not always possible, especially if the actions are continuous. And so we need to integrate over all of the actions, which is intractable. So they use another trick. So basically, they replace the whole thing using estimation like this. And this is their intrinsic reward. So it's basically the log of a probability, which is very similar to softmax. So basically, it says that if my chosen skill Z, which is basically here, if my chosen skill Z gives a much better prediction of what happens next compared to other skills, then it's a good skill. Okay? So if my skill Z, again, gives me a better prediction of what happens, so it means that if I'm sure of what's going to happen, if I'm sure of the next state that I'm going to reach, compared to other random skills, then this is a good skill, and I want to reward it. And this is like the motivation behind this reward estimation. This reward encourages each skill to model different dynamics. So basically, a dynamic is just a transition, okay? So if we try to model different dynamics, it's basically saying that we want to learn different transitions. One skill might, for example, predict turning left. Another skill might predict jumping well, etc. So each skill is going to present a certain form of dynamics. Again, you have the pseudo algorithm and the figure, which is hilarious because they use exactly the same figures, like the same style. So yeah, Diane was in 2018, and that is newer, kinda, but it's pretty old in the literature, so it's in 2021. And you can see that they only added this conditioning over the mutual information. Very similarly, so we sample a skill Z, and then we just compute this intrinsic reward, and we maximize it using a reinforcement learning algorithm. What's interesting in DADS is that we can use any reinforcement learning algorithm we know. We just need to maximize this intrinsic reward. In Diane, we need to use soft actor critic because we had the entropy maximization term, which is only available in soft actor critic. But for instance, if you take PPO or something else, then you're not necessarily going to have that term. And so, yeah, that is able to use other algorithms because it only needs to maximize a certain reward. Just a table to compare. So in Diane, we don't use the dynamics of the world model. It means that we don't care about going to the next state, etc. We only need to care about the current state and the scale. But in that, we take that into consideration because this is the extension of a Diane. In Diane, we try to maximize the diversity based on the states, whereas in DADS, we try to maximize it over the transitions, over the dynamic model. All right? In Diane, the discriminator is basically a log probability. In that, it's a likelihood ratio from the dynamics model, which is basically this in here. It's just a ratio of the ratio of one skill over the other random skills. In Diane, we care more about where we go because we try to maximize diversity between, or to maximize the mutual information between the state and the scale. But in that, we care more about how to move, how to go into certain stuff. So if we have a goal, Diane is just going to learn how to reach it, kind of, but that is going to try to reach it in different ways because we take the transitions into consideration. Okay, so this was for the skill discovery. category. Now we move on to the intrinsic motivation category. Okay, and it's going to be much, much easier now. Actually, this is really cool, and I really want you to understand this. There is a paper called ICM, which is basically curiosity-driven exploration by self-supervised prediction, which is some sort of an intrinsic motivation that we try to give to the agent. So basically, we are kind of going to reward the agent for its curiosity. So if the agent is going to explore a new state that hasn't been explored before, then we are going to reward it because it's curious to learn new stuff. But if it goes to a state that has already been explored, then yeah, we don't care much about that, and we're not going to reward it. So how do we know if we already explored the state or not? In the discrete case, it's quite simple. You keep a history of the explored states, and once you have a new state, you go check if it has been explored or not. If it has been explored, just return a reward of 0. If it has not been explored, then you return a positive reward to kind of thank the agent for exploring that. Okay? Now, for the discrete case, it's quite easy. Now, for the continuous case, for obvious reasons, we can't have a history of all the explored states, and so we need something that is more sophisticated. To do that, they use a very brilliant trick using what they call a forward model, which has the goal of trying to predict what is the next state. Okay? Now try to focus with me on this one. Imagine that we have a model that is initially randomly initialized. Okay? And so this model takes, I can just write it in here. So let's call this model F. It takes S as input, and it tries to predict the next state. Okay. Wait. So Fs. It tries to predict the next state. Now the model is randomly initialized, right? So in the very beginning, when we try to predict what is the next state, and we compare it to the actual state, then the difference is going to be very big, right? Because the model is new, it doesn't know anything, and so the difference is going to be very big. And thus, the reward is going to be just the difference between the prediction and the actual value. And there's going to be a big reward because it's a big difference, because it's new states. But now imagine that a certain state, I have explored it many, many times. Okay? What's going to happen is that every time I explore it, I predict with my model, but I also update the model by minimizing this, right? And so if a state has been explored many, many times, then I have updated the model to predict the next state correctly many, many times, right? And so the prediction error is going to be very small. And thus, we are going to return a very small reward. And this is the idea. If a state has been explored many times, then the model has been updated many times to predict the actual next state, which means that we are just going to return a small reward because it's small difference. But if a state is completely new, then if we try to predict the next state over a new state, which the forward model has never seen before, then the prediction error is going to be high. And so it's going to be a high reward. And this is basically what ICM does. So they train a forward model to predict the next state as prime. Given the current state S and action A, uses the prediction error, which is basically how wrong the forward model is, as an intrinsic reward, which is basically the motivation. So curiosity in this case is going to be defined as how surprising the next state is given what I expected. Again, in the very beginning, we have the policy that is exploring the environment, and we have another model, which we call the forward model. This forward model is going to take the current state and an action as input, and it will try to predict the next state. Now, if a state has been explored many times, then the model is going to correctly predict the next state, which means that the prediction error is going to be small, which means that the reward is going to be small as well. But if the model falls into a new state that it has never seen before, then of course the prediction is going to be different than the actual value, and so the error is going to be big, which means that the intrinsic reward is going to be big as well. This is for ICM. Now we have another paper called R&D, which is exploration by random network distillation, which is very similar to ICM, but it is like more clever. So we say that no need to try and predict the next state, but rather we are going to try to predict a random value. So they say that they are going to use two networks. One is called the predictor network, and the other is going to be called a random network, which is fixed. Okay, so we have F and we have F hat. So F is a random network that is fixed. It's not going to get updated. And F hat is another random network, which is like different than the first network, but we will try to update it. And we will try to update it in a way that it's going to predict values that are very close to those of the random network. And so again, if a state has been explored many times, then we would have done this update many, many times. And so the prediction error is going to be small, because now F hat is going to predict something very close to the random network. And so the reward is going to be small, which makes sense because this state has been explored many times, so we don't want to explore it again. But if a state has not been explored and it's totally new, then F hat has never seen it before, right? And so the prediction error is going to be big because we never had updates over this state. It's like an out of distribution state, right? And so the prediction error is going to be high, and the reward is going to be high because the state is new, and so we are going to reward the agent for exploring this state. And they use the notion of novelty, which is basically very close to the notion of curiosity. So novelty is basically how different the current state is from what I've seen before. Okay? And yeah, so this is for ICM and R&D, which are basically key methods in the intrinsic motivation family. I wanted to introduce more methods, but I know I didn't have enough time to do so. So I think that's it. What we've seen so far is an introduction to unsupervised reinforcement learning, which is a fascinating field. And what I liked most about it is that every single paper brings a brilliant idea to tackle the problem. It's just fun, you know? Maybe it's not very useful currently, but it's just pure genius work. And it's amazing. And we said that in the unsupervised reinforcement learning family, we have like a lot of subfields. We have the skill discovery one. We have unsupervised goal condition reinforcement learning. We have the state coverage, which is quite different. And we have what we just saw, the intrinsic motivation ones. And it's a very active field of research. I would really advise you to take a look at it. It's really fun. And yeah, I think that's it. So I would love to thank you for the invitation, and I really hope that you enjoyed it as well. Yeah.
Yeah, sure. Thank you very much, Nazim, again, like for the very insightful topic. It's new, I believe, for me and for many people, like being here, because like the motivation for us all was like let's go out from supervised learning. We have something really cool. We have an environment. We have a reward. Let's do error. And then now we see like this.
Yeah. It's like it's an extension of reinforcement learning, and God knows what's gonna come after that. So
yeah. Super excited. Another thing to look up for after reinforcement learning.
Yeah.
So we kind of So we kind of move to some questions from like the audience and from me. Well, I have a question regarding like the intrinsic motivation forward model. The user forward model, I believe it will be updated within like the interaction and behavior of the agent, and also like something maybe similar to a surrogate model or something like that. I'm curious about how this model is trained effectively, like maybe in continuous spaces of states, or that we can maybe know that the model is actually like modeling the behavior of the agent that's currently following, like
Mhm.
for instance, its curiosity, or just like underfitting. Like how such like surrogate models are trained effectively in such manner.
Okay, so yeah, let me just go back to the slide. I feel like we're missing something here. Maybe I didn't explain it as well. But in the intrinsic motivation family, we no longer talk about behaviors. We talk about exploration. We actually call them an exploration policy. Okay, and
Mhm.
the goal here is not to learn distinguishable behaviors like in skill discovery, but rather to
Mhm.
try and explore new states. Basically, we try to explore as
Okay.
much as possible from the environment. Because if you take, for example, in traditional reinforcement learning, there is no
Mhm.
guarantee that you are going to explore the whole thing, right? Basically,
Yes.
you can just kind of overfit over a certain trajectory. And so,
Mhm.
in intrinsic motivation, that's the goal. We don't talk about behaviors generally. Now, the forward model is going to be just a neural network, and we're
Mhm.
literally going to do supervised learning here because um, S prime hat is the actual next state returned by the
Mhm.
environment, which can be seen as a ground truth. And S
Mhm.
prime is just the prediction of the model. It's actually the other way around. S prime is the next state given by the environment, and S prime hat is the prediction of the forward model, right? And
Mhm.
we try to minimize this distance between it. It's just like an Euclidean distance, nothing more.
Okay.
It's just a regression. And so that's the beauty of the method because it's actually very easy to use, right? And
Mhm.
so yeah, I don't see like any problems that can occur in here. And what's really brilliant in this is that we actually make use of the weakness of neural networks because neural networks are
Mhm.
very weak against extrapolation. If you have an outlier or an out of distribution variable and you pass it as input, then the neural network is going to predict something completely different, right? And
Yes.
so that's the same thing in here. If we explore a new state, it can be seen as an outlier or as an out of distribution input. And so the model is going to return something completely different. And you're going to make
Mhm.
use of that because if the model returns something completely different, it means that,
Mhm.
yeah, it's a new state. And so you're going to make use of that. I mean, yeah, it's formulated in a better way now. So that's the
Mhm.
beauty of such methods. We make use of the weakness of neural networks.
All
The same
right.
thing for
And
NLP. Yeah.
mhm. Okay, I will save a question maybe after the audience questions.
Okay.
Uh, the next one says, how is exploration exploitation handled in such field, given that we don't have the external reward?
Okay. Um, Let me give me a minute. I don't think it's handled any differently than traditional methods. And that's again one of the strengths of such methods because we keep use of exactly the same methods. So we have PPO, we have soft after critic, we have the same algorithms, and we keep using them. So the only thing that is going to be different is the reward that we try to maximize. Now, we might say that the goal is to try and learn diverse behaviors, which can leads us to think that yeah maybe we need to use more exploration than exploitation, but that's not true because if we only rely on exploration then the skills may not be as distinguishable as we want in the case of skill discovery methods because we want them to be distinguishable. And so there is also a part of exploitation in here because given certain skill I want to reproduce the same behavior. and I want to explore something else, right? And so there is still a little bit of exploitation. And so, as far as I know, in the papers, they don't even talk about this problem of exploration exploitation. For them, it's not our problem. It's a problem of reinforcement learning algorithms. And in our case, we don't touch that. We only use it as it is. We just like take care of something else. So that's the idea. We can tackle everything at once. So we just say that, yeah, this is figured out already. So we just move on.
All right.
Yeah.
Next one saying, at the beginning you mentioned having many goals. Does it mean that we have some sort of objective function to evaluate? And how good do we reach each goal, or is that considered a reward in itself?
That we have some sort of objective function to evaluate how good do we reach each goal, or is that considered a reward function? Okay, that's actually a good question. In short, reaching a goal is itself a reward, but it's very sparse because once you reach the goal, it's going to return a reward of 1, for example, and if you don't reach it, it's going to be 0 every time. So in unsupervised reinforcement learning, or basically in unsupervised goal-conditioned reinforcement learning, we make use of that. We don't have a reward function that is shaped in a way that is going to take us to a certain goal, but once we reach the goal, we say that, yeah, we had a reward of 1, and we try to make use of that. So what's interesting here is that each goal can be seen as a skill because reaching the goal is a different skill. So you have different goals, implies you have different skills. And so, yeah, maybe you can say that the intrinsic reward in such methods is if we can reach a certain goal or not. Actually, what I'm working on right now is instead of reaching different goals, I try to scale up the problem and I try to reproduce different trajectories because reaching a single goal is kind of limited and it doesn't tell you how do you reach the goal. But if you try to reproduce a trajectory, then you're not only going to reach the goal, but you can reach it in different ways. So for example, if you have a maze, you can either go down, go up, do a circle, and then go to the goal, etc. So that's some sort of extension, yeah.
All right. Maybe the next question I have, like, for example, in goal conditioned like era, we have this notion of a goal. And maybe we can know that we have reached a certain goal, we did the task, and it's all good.
Yeah.
And here, like for the two methods that were presented, the first one, the skill diversity, it used like the notions of entropy and like the mutual information and like we know that it will explore and it will figure out some skills. It will figure out how to acquire those skills that will be distinguishable and everything. For example, here in the intrinsic motivation, like it motivates basically the exploration of the agent, but like for all of these they kind of like design a certain intrinsic reward that does the job for the two methods. But what guarantees that these skills or such exploration actually is useful, like overall in any type of like environment? Because I kind of like feel that where will be like the advantage when we actually have the maybe the extrinsic reward or we want to do something, like how does these methods help and guarantee that we will have like valuable skills or useful skills for the agent?
Yeah, that's an interesting question. I don't know if it is bold of me to say this, but I think that there is no guarantee that the skill that you learn can be of use once you have an extrinsic reward. But we hope that the skills that we learn is going to be as diverse as possible in a way that we are going to cover the space of all behaviors in a certain way, right? So for example, in Health Cheetah, the environment gives you a reward to move forward, okay? So in the skills, we try to move forward, move backward, jump, crawl, do everything. Hopefully that by the end, we are going to kind of cover the actual skill, you see? But yeah, you're right. If you don't have access to the extrinsic reward, we can't know beforehand whether the skills are going to be of use or not. And so, yeah, I think that's the main reason why we want to have diverse skills, because hopefully we want to cover all the space of different skills. Okay?
Yeah. And how expensive is that? Like we know, like for some tasks, even
Uh-huh.
like doing error with the
Yeah.
extrinsic reward is super costly, whether in time, in compute, and everything. But like now we kind of like using like it's a higher dimension of doing error.
Yeah,
Like
yeah, yeah, true.
how expensive is that?
Actually, they don't care. They don't care at all about how expensive it is. You know, in the papers they say that don't worry, the environments are built using JAX, and we know that JAX is super fast. And so yeah, let's not care about computational overhead. Let's just run everything on multiple GPUs and see the results. So yeah, it's quite expensive because not only you try to learn one skill, you try to learn all the different skills. And so yeah, but I think nowadays, yeah, maybe 2 points in here. The first point is that the benchmark that they use is quite fast because, for example, we use Half, Cheetah, Walker, etc. So they are pretty fast because they are simple environments. We only have an agent, and the goal is to move in the environment. And we rarely see these methods work on complex environments, for example, in, I don't know, code optimization or anything else. So that's what allows them to run these methods like efficiently. The second point is that we're reaching a point where execution time is not a problem because we have super fast GPUs and the libraries that we're using are super fast and super optimized, like JAX. And so you can run, for example, Half Cheetah using like literally 10,000 parallel environment at once. And it works on my computer. So it's very, very efficient. And so, yeah, basically, we don't care about that. I think it's a problem for later.
Okay, yeah.
So,
And like linking to that regarding the benchmarks, like what are all maybe environments or use cases that these methods were applied and have proven to be useful?
yeah, surprisingly, they use a lot of mazes because in a maze, especially when it's very complex, it's quite hard to reach like some goals in there because they're kind of hidden behind many walls, many turns, etc. And so they use mazes, even though it looks very simple, but actually mazes are the hardest one to solve because if you have a maze that is very complex with a lot of walls and turns, etc., it's kind of hard. But they also use it on continuous tasks, like I showed you, like Half Cheetah, Walker, Hopper, stuff like that, like very classic benchmark.
Mm-hmm.
And maybe I'm missing something. I think that's it for skill discovery. They're using like very simple environments and very efficient ones. Yeah. Maybe
Okay.
one thing I didn't that I didn't talk about, and you actually asked it. What do we do once we have an extrinsic reward? The easiest thing is that we are just going to evaluate all the skills with this extrinsic reward to see how much cumulative reward they can get, and we simply pick the best. Okay?
Mm-hmm.
But this is like the easiest way to do things. And it's not very efficient because imagine that you have an infinite number of skills. You're not going to evaluate an infinite number of skills. So we try to find that it's very active for now, but we try to find ways to do zero-shot reinforcement learning. And it's actually another field. It's called zero-shot reinforcement learning, meaning that once you have a new task, then you can solve it in zero shots. It's like in ChatGPT. You ask it a question that it has never been trained on, and it can generalize and find a way to answer the question. It's the same thing in reinforcement learning. You give it a reward function that it has never seen, and you try to maximize it. And that's just like next level reinforcement learning for now.
Oh, okay, great.
Yeah.
And in skill discovery, if I'm understanding right, like once we have the extrinsic reward, the agent can kind of like couple multiple skills to solve it.
I'm not sure about couple. It just selects it kind of selects one of the skills and use it.
One of them.
Yeah, it's kind of but if you do some sort of interpolation between them, then you're probably going to have like, I've seen it in one of the papers. I don't remember which one, but
Mm.
they say that if you take two skills, for example, this skill takes me here and the other one takes me here, and I do like an interpolation between them, then I can reach the region that is between them.
Oh, okay.
So kind of like that, yeah. But I would say there is no guarantee for this behavior because we didn't like explicitly put this in the objective function, right?
Mhm.
So it's just like neural networks' nature to interpolate because they are continuous, so it's easy to do interpolation. But there is no guarantee for this. Yeah.
Okay, okay, I see. Uh, I believe it's all on my side. Also from the chat.
Mhm.
Okay, we have in 1 hour and 10 minutes. Uh, I would say again, thank you very much, Nazim.
Pleasure.
It's been really exciting to explore something totally new,
Yeah.
and I believe like the excitement has been yours as well. Like diving into this and like
Yeah.
giving
Yeah.
it like to the community back. So this is super appreciated, and this is like the thing that we keeps us like updated and motivated and all. Like
Yeah.
we
Sure. Sure.
branch, we explore, and then we get all together. Uh, yeah, thank you very much.
Thank
It's
you.
always a pleasure to have you in School of AI. And thank you, everyone, for being here, for your questions. And I hope you enjoyed, as well as like the next conferences that we will have in AI Summit. So have a great night, and thank you, everyone. Bye bye.